So it's 45, okay? Remember last class, guys, focus. Last class we talked about the horizontal asymptotes and the slant asymptotes. The class before that we looked at like vertical asymptotes and holes. So we've done a lot so far in the last few concepts with the idea of what graphing rational functions will look like. So in a minute, we're going to talk about intercepts, another key point when we graph rational functions. For this kind of a problem, John, one light, please. Just one or two. For this kind of a problem, the question asks us to determine, for the first case, the y-intercept. Sorry, Juliet. So, if you remember, you got to have this memorized, and if you don't, you need to write it down in like big, big, big letters, please. That's got to be memorized at all times. You want to find the x-intercept, set y to 0. Find the y-intercept, set x to 0. No matter what kind of a function you have, it does not matter. If you want to find an intercept, set the other variable equal to 0, always. Always, always, always. Good. So, write it down. Okay, the first two are going to be very simple, and you're going to notice that. The y-intercept is very easy. The x-intercept is a little bit tricky. So we're starting with the y-intercept. So, Derek, what should I do here? All right, good. It says find the y-intercept. When something says find the y-intercept, it means set x to 0. So we're really doing g of 0. It's like we're running a table and we're putting a 0 in for x. Well, what happens to all those zeros, guys? All these x's that you see, what happens to all those locations? They all drop off, really. And what are you left with? Very good, Daniel. Negative 3 over positive 6. You're going to have 0 plus 0 minus 3 over 0 plus 6. I don't care if it's squared, if it's cubed, if it's the 10th power. If you plug in a 0 for x, it drops off, okay? Again, just keep that in your mind. So negative 3 over 6. What's negative 3 over 6 as a decimal? Negative 0.5. So what's my y-intercept going to actually be as a coordinate?
0.5.
Very good, Derek. 0, negative 0.5. Make sure you make that statement. I know it sounds really trivial, but you know how many people just have this here, and then they forget that it's y-intercept, and they try to make that into their asymptote? It's very, very misleading. You might get an answer like a 2 here. And lately we've been doing stuff with horizontal asymptotes, where it's like y equals 2. And a lot of people, you know what they write? They write y equals negative 0.5. Because this is the y-intercept, isn't it? But that's not y equals. Again, if I ever write down, I'm going to write a little side note up here. If I ever write down on my page like y equals 2 or y equals 7, those are horizontal lines. That's what they are. Remember from horizontal asymptotes, that's what they look like. So if I ever write something like that, I'm going to think you're talking about a line. But when you write it as a coordinate, I clearly know that you're talking about the y-intercept because x is equal to 0, and I can see that. But if you simply had written down y equals negative 0.5, I don't know if that's a line or a point or what's going on. So you want to make sure that you're clear with your mathematical representation. And that's what I've been putting on your last few quizzes. So when you have a hole, for example, in the graph, when there's the vertical asymptote or a hole, for the examples when there's a hole, you need to not only locate the hole in the x-coordinate, but then plug it back in to the simplified form so that you can also find the y-coordinate. So I want to know the location, for example. Or for the vertical asymptote, I want to see x equals 3. Well, that's a vertical line going through x equals 3. Okay, that tells me what it is. On the ledge. I've had that one for like a month now. Push lane, it's a new kind of sharpener, or it's an older sharpener. On the ledge. Julia.
I have a question. So, like, when you have that, you already have a form, you plug the y in, right? You plug it into the x, right?
Into the simplified form, though. Once you cancel out the factors that repeated themselves, that's when you plug it back in.
You plug in like 0, right?
Well, you plug in whatever the hole would have been. Okay. That's for vertical asymptotes. Concept 43. Okay, 43? Yeah. All right. So that's my y-intercept for this one. Let's take a look at the next one. Now, what I'm going to do today is talk about some word problems, and in a minute we're going to talk about velocity problems. They show up in calculus a lot, so it's a good form to get your brains going ahead of time. For this one, it says that a stock's value in millions is represented as a function of time. F of t equals, and the function is t cubed minus 3t plus 7 all over quantity 2t plus 4. And this kind of a problem is asking for us to determine the initial value of the stock. The initial value of the stock. What does the word initial mean to you right away? What is it? Beginning. Who said that? I can't hear. Beginning. This is the beginning, okay? The initial value. So, if I said to you, when you were born, what was your initial weight? What was your initial weight? 7 ounces.
8 pounds.
8 pounds. All right.
That's very diesel weight.
25 or 35?
25 pounds.
Okay.
Okay.
So, most people are born around like between 7 and 10 pounds, right? Between 7 and 10 pounds total?
10 pounds.
So, initial though meant what? When you were born. So, if you started counting in your lifetime, how old are you when you're born?
0.
Are you 0 when you're born?
What
a few seconds. I know. Ignore the pregnancy, guys. For real, but think about time. Right now, when you have your birthday, anybody's birthday coming up?
Mine's in November. Mine's in September.
2 months?
Mine's in April.
Right.
November.
That's not coming up.
December.
Really? May is
January.
Wait.
You're both in May?
Mine's April.
So,
I had the best birthday ever.
on your birthday, you turn a certain age. Now, for example, say you turn 16, it means that you currently have lived 16 years of your life.
That's what 804.
Okay, you've turned 16 years of your life. Relax. On your first birthday, you've lived 1 year of your life, right? That's what your first birthday is? So when you're born, it's like your 0th birthday. You know, it sounds weird, but think about it logically. On your first birthday, you've lived a year of your life. When you're born, you haven't lived any of your life yet. You've pretty much just been born. So theoretically, you're 0 years old. So whenever something says, find the initial value, and it's a time problem, what are you plugging for time? 0. Okay, which in this case really means find the y-intercept. Again, if I plug in a 0 for t, isn't that like I'm finding the y-intercept like I just did? I'm really doing this. Okay, so go ahead, plug a 0 in, reduce your fraction, give me your y-intercept, please. Okay, remember that initial time means time equals 0. Plug in a 0 for t, which is like you're finding your y-intercept here. So that's my coordinate. What should I really do with my answer now? And go back to the original problem. Okay, plug it back in, but what do you mean by that? I wouldn't plug it back into the function. Go back to the original problem. What does it say about the stock's value? What is it measured in? Millions. So that's really $1.75 million, isn't it? So if I were to actually be asked to determine the initial value of the stock, it's not really saying find the whole coordinate. It says value. Find the value of the stock. What's the value only? Very good. The y coordinate. Remember, value always, if you say find the value of a function, it's saying find the y value. So this is $1,750,000 really. Because again, this is 1.75 million. Okay, 1.75 million really means $1,750,000. And think about that logically. Okay, a million is times 10 to the 6. So you move this decimal over 6 times. So the decimal was here, where I'm pointing to right now, right here, and I moved it over 6 spots. That's where that number comes from. Because a million is times 10 to the 6. Think of it as scientific notation. So again, the problem asks for the value. That's why we only give the number. If you were finding a y-intercept, you give the actual coordinate. I listed it because we're going to try and be consistent here. Okay, but you want to give the value of the actual stock. Let's go on to the x-intercepts now. So again, y-intercept, very simple. We drop all the x's off. We look at our fraction that remains. Now let's take a look at the x-intercept. For the x-intercept, what do I have to set equal to 0? The y. And don't say x, guys. It's the x-intercept. You got to think of the other coordinate, the y value. So please go ahead and start by doing that. Can I get some suggestions as to what to do next?
And
Can you?
multiply by.
Yeah, I mean, you can multiply both sides by 2x, right, to drop it off. Before you do that, though, I'm going to show you a little trick, and it helps you in the long run. Factor the numerator first. Factor everything before you can do anything else, always. Always, always, always. Factor first. So let's start by doing that. And I know it sounds weird, and I would agree with you, because the 2x is not going to have an issue, but you're going to see in the next problem where it does come into play, the denominator. X, say again?
X minus
Very good. The reason I'm asking you to factor the numerator is because it might be able to reduce. And if you can reduce it, what do you have there if you can reduce something? What do you have? A whole. Remember, whenever there's a factor that repeats itself in the top and the bottom, or a common factor, common just means it's in both, whenever there's a common factor, you can reduce it and there's a hole there. Well, if there's a hole there, you can't have an x-intercept there. So it won't affect the problem. But for this example, there's nothing that repeats itself. It looks like 2x and x plus 2 are similar, right? But that's not the same factor. So you cannot reduce here. So the next step, as Andrew said, is to say, well, get rid of the 2x. You can think of that as cross multiplication. If you put this over 1, or just remember, as we've done this many times, whatever the denominator is here, take it and bring it on up over here. It always works, just like v equals d over t. Remember v equals d over t for velocity, distance, time? You can always move it on up. So move that up. What do you get here still, though?
0.
Because 0 times 2x is still 0. So you end up getting 0 equals the numerator. So what do we really care about then? What we really care about to find the x-intercepts is the numerator. The numerator. Unless the denominator happened to be the same as the numerator, then we would have to show that there's a hole there. Okay? Again, what we really care about is the numerator. And if I have two factors, how many roots must I have? And they are? 5n, negative 2. Jay? Yes? Yeah, I could tell by the way he was asking the question. So x equals 5 and x equals negative 2. Those are my roots for this function. Okay, those are my roots for this function. Remember, for this kind of a function here, the denominator can play a role. It really can. But in this kind of a problem here, we're going to see that it doesn't, because it doesn't repeat itself. In a minute, though, we'll talk about what happens then. So I've got one root at 5, and I've got one root at negative 2. Is that clear?
Yeah.
So how can I summarize now? What's the important part of the fraction?
The numerator.
The numerator. Okay, again, to find the roots, you're really setting the numerator equal to 0. That's what you're really doing. Okay, but you have to check the denominator to see if the denominator can cancel the numerator first. That's why we did that check. We factor first, and then we can set it equal to 0. Juliet?
So basically, if there's a hole, then all you do is just leave it like
You
that.
ignore it for now. You would have already analyzed the hole, because you look at the hole in the vertical asymptote, and you look at the horizontal asymptote, and then you look at the intercepts. So once you've already analyzed the hole, you don't have to worry about it as a root. It's not going to appear as a root, and that's the whole idea. And we're going to show graphically how that works. Okay, but again, for now, you're going to ignore it as a root if it comes up that way. All right, let's look at another one. This is a problem that is, and I'm not exaggerating when I say this, it's on 80 calculus exams. This problem right here. Okay, it really is. A particle's movement is represented by the velocity function given by v of t equals, now the rational function is the following. Quantity t squared minus 5t plus 6 all over quantity t minus 2. Determine when the particle is at rest. Determine when the particle, so you can think of like a photon, an electron, a neutron.
Are they ever really at rest?
What's 0?
Minus our breath.
What does 0 mean?
It's not moving. It's not moving.
Good, 0 what though? You're saying 0. I need some
Zero
sort of
velocity?
What is it?
Zero velocity.
0 velocity, thank you. Juliet, 0 can mean 0 time, and that's initial time, isn't it? Initial value. You gotta give yourself a unit here, please. With some sort of a label. So when we're looking for this kind of a problem, we want to know, again, as John just said, when the velocity is 0. So go ahead, set the velocity equal to 0. Well, that is, that's the whole thing. And the other one that you reduce, the thing that you canceled out there, that's where the hole occurs. And that's what you use concentration.
If you change t to 0, does that mean you're changing time?
Exactly, and that's not what it asks for. That would say, what's the initial velocity?
So,
Again, guys, two different problems. If it said find the initial velocity, you would plug a 0 in for t to find the velocity when time equals 0. But this says find when the particle's at rest, which means set the velocity equal to 0. So go ahead and put a 0 out here now, and set the whole thing equal to 0.
So just T minus 3 between velocity and rate.
Because remember, this is the value of the velocity at a given time. This indicates the value of the velocity at a given time. Well, we're saying that the velocity is 0, find that time. Okay, determine when. When you see the word when, it means solve for time. Determine when. You've got to be finding t here. If it had said find the initial velocity, that's where you would drop off the t's instead of equal to 0.
So would it be 3?
Would it be 3 here? Why, where are you getting 3? I see that there's 2 answers though.
Oh, because, yeah, it's if I factor, it's T minus 3 and T minus 2.
Very good. Factor the numerator. Here's what you get. Which clearly tells me that I have a hole at t equals positive 2. There's a hole. Again, because a 2 minus 2 would give you the 0 here, right? So t equals 2, which you would think would be a root from this, is actually a hole. So in this case, time equals 3 is when it is at rest. After 3 what? What would my units be? Oh, I didn't give units, actually. I'm sorry. I apologize. It would be seconds, though, yeah, for these kind of exams. Here's how... John, stop talking. Here's how you'd have to do this. If you were given units, so it said velocity in meters per second. That's what it should have said. So if you see meters per second as your velocity, then you know your time is seconds, because it says it right there in the denominator. Again, meters per second, meters per second, meters per second. Physics calculus, use meters per second. Okay? You'll also see feet per minute sometimes, so keep that one in mind, but this is the general one you use. So again, just to clarify, let's make sure we understand, at time equals 2, what is there again?
Yeah.
A hole. Again, there's a hole there, not a root. There's no x-intercept there anymore because there's a hole there because of the fact that we had the same repeating factor on the top and bottom. So we're still using the stuff that we did with vertical asymptotes and holes here because we have to actually take that into account. You're learning right now more than the juniors learned last year and more than the seniors are learning this year in pre-calc rational functions.
Wow.
Okay, I'm teaching you more than they're learning, which is a little bit exciting to think about. Okay? What's up, dude? Go ahead.
God, so much more.
There will always be a hole, right? Because you only have to get one.
Well, there's only a hole when you have the repeating factor in the top and the bottom. It could be resting more than once, believe it or not. And that's where, imagine if a velocity of a particle followed a wave. When it follows a wave, it has many resting points. It like moves and it stops, and it moves and it stops. Imagine an object on a spring, and you extend it, and you let it go. It would start to oscillate back and forth. Every time it comes to the end, it has to stop. And then it comes back, and then it stops. And then it comes back, and then it stops. Let me show you an application of that, because that was a really good question. Okay, so a very simple example of this. This is where you see this in calculus. They talk about an object that's suspended or attached to a spring, and that object has some sort of oscillatory motion or periodic motion. It waves back and forth. And what you're going to notice is this. Take a look at the mass at the end of the spring here. When it gets, pick it up, when it gets to the very bottom of its path, it has to freeze, and then it goes back up. And then it gets to the top, and it freezes right there. Then it comes back down. So at these periods, or at these locations of time, is when the velocity is 0, when its motion stops, and it's periodic. It stops, ready, now. Then it stops at the bottom, now. And it continues. So these kinds of problems, you have sine and cosine waves. Because sine and cosine waves, we're going to look at this year, are periodic functions. And that's how they're represented. But this is a very good example of where you would see an example in AP Calculus where we're looking for the velocity equaling 0. And you're going to see a wave that, Trayvon, can you do it again? Yeah, its motion looks like that. Because what you're going to notice about its motion, if I can actually draw it. What you'll notice about its motion is that the motion of the particle actually follows a sine wave, which looks periodic. And we've seen these before. Even if you look at like radio waves or anything like that, the shape they take.
Well, like the thing on the, when you're tracking the heart?
Yes. Like the,
Heartometer.
what is it? Is that what it is? IKG? EKG?
They use one on M1, that's why.
I don't know. So it's at the origin. Listen. Guys, come on, focus up here. It's at the origin, it's not moving. It picks up, imagine this is velocity. It picks up velocity. Its velocity becomes a maximum up here. Then it starts to slow down, and it stops because the velocity is now 0. Then the velocity becomes negative until it gets to a minimum velocity in the negative direction. Then it starts to increase its velocity until the velocity then again becomes 0 here at the root. There's my velocity equals 0 there. Then the velocity picks up again. Its velocity becomes a maximum. Get it or not? Come on, don't miss. Now its velocity is a maximum. Then its velocity becomes 0. Where is it?
I don't see it.
I don't know what they're talking about.
There's a gnat in the room. He's fine.
It's a freaking gnat!
It's not a protein gnat.
Abortion.
Example 5. Saying that, guys, it was going to bother everybody the whole period. I would normally just count it right out.
You didn't make that gnat just to
I
have.
hate it, you see me?
What are you, an Indian now?
Let's take a look at the next example.
You're taller than me? You can be older than me. Okay.
So she talking about
Make me angry.
Be careful with this example, please. Make sure you factor completely. Again, you're always factoring completely. It says what are the roots, which really means what is the x-intercept. What can you factor out of the numerator immediately? X. Please, please look for that. Whenever you see the x at the end here. And that makes it a whole lot easier to now factor the rest. Luis, what do I get when I factor the numerator? Factors the numerator? It's funny how Luis has 12 voices. I'm talking about everybody else that answer when I said Luis.
Where's the hole?
Very good. Where's the hole, guys?
-3.
Positive 3. Again, there's the hole there. Remember, the hole is always at the location that causes the denominator to become 0. What am I left with? So what are my roots, everybody?
9 and 0. -9 and 0.
Good. -9 and 0. Remember, you always have a root at 0 when you have a factor of x. People seem to forget about that a good deal. Even on their concept 42, 43, 44 quizzes, 43, 44 quizzes. Please, when a factor has a factor of x, its root is really 0.
Whoa. It's always not 0 for this one, because the x repeats itself. And the x plus over 0, right? So that means the whole there. You have to take 0.
Hey, Lauren, do the wave.
Do the wave. By the way,
Hey, tell them.
Time to go back and forth. Ready? Let's go. All right.
1, 2, 3.
Last one, last one.
Up and down on boogie.
No, sorry. Try the last one on your own, please.
Oh my goodness.
I got this.
Use your logical thought processes here to factor the numerator. Think about what you need to do. Go ahead and practice, please.
Excellent.
Again, read the directions for this problem. You determine the zeros, so the roots, and the y-intercept both. So if you want to start with the y-intercept, you can, or start with the roots. Pick on your own. Still stretching my legs.
Kevin Hart.
I'll go everyone in here tonight.
He's still doing it.
I'm not going to stop.
Are you so
Think about the older concepts we did, where we had to factor something like that in the numerator. We've done this before.
Yeah.
Kids nowadays. So hostile. I'm getting new glasses. In August. Give me
Yeah, you guys hear that?
I can hear it.
Alright, seriously?
That is outside. The other one was that one, the light one, is going, Papa, is that you? If you're stuck, please raise your hand, guys. Don't just sit there.
Everybody that was a part of
All they said, so what I'm trying to
Hey, you. I see you. Hey, you.
So when you
It's great, didn't
Guys, you're hitting a synthetic table. If you haven't picked up on it by now, you need a synthetic table to factor the numerator. Please go ahead and do that. You're going to have to do it twice so you get down to a quadratic so you can then factor on your own.
Hey, you. I see. That's why I had to.
No, you can't work out factor. Guys, denominator, you need AC method for the denominator.
I got this one. Watch this.
You need synthetic table for the top, AC method for the bottom.
Oh, so you can't just do that. I was going to do AC method, but you can't do AC method.
You can. Now use AC method on this.
I'll put it on next week.
But it's going to take a lot of people.
Yeah, it's gonna be I guess.
I do that. Impression.
So you get to zero.
You there. It's now your turn.
I think you had a hiccup or a tattoo.
You there. You there. Later. That's why I had to
Crazy.
1, 0, 0, 1, Rat, rat, rat.
Programming.
Add up to 7.
So we didn't say that since like freshman year, dog. So what happened to chowder, man? They took it out. What happened to what? Oh yeah, I heard it says that you make kids fat, like curve kids
Think of those basic facts as basic.
Isn't it 8 at 1?
I hate losing my shirt off.
This is the ball.
Yeah, that's why I heard. SpongeBob? Oh yeah, you're grabbing batteries. I don't eat a lot. No.
I want to get batteries at Costco, so I told John I would.
They fixed the one I'm sorry.
I'm going to try and get them something that's all favorite.
Yeah, they said Barney. They said the same thing about Barney too.
Barney? Yeah, all the autistic kids singing.
Come on, man. Give me my bag.
Got your 2 factors.
You look good. It's a lot of good clothes inside. Much of it.
So what do you do?
Correct. But I want factors, so write factors now. Those will be the roots. Then I can't tell you. I'm going to do the y-intercept up here. That's the easy part for now.
All the 49.
It can't be 2. 2 is even.
So what does that mean at the board, guys, right now, for this problem? That's the y-intercept only. Okay, I didn't do the root yet. That's the harder part. You're all working on right now. The y-intercept, I just need to set x equal to 0, right? So I set x equal to 0. I plug in all my zeros for all my x's. But I end up getting 30 or negative 30 over 0. But I can't divide by 0. So in this kind of a graph, there is no y-intercept. And that's possible with rational functions. It does not exist. Okay, it does not exist. Yeah, exactly. It's going to be on one side of the axis or the other. And the idea is because there's actually a vertical asymptote at x equals 0. There's a vertical asymptote that goes along the y-axis. How come? Because I can factor the denominator. I can factor an x out of the denominator. And once I factor the x out of the denominator, it tells me from concept 43 that there's a vertical asymptote at x equals 0. That's the reason why it doesn't exist. So you're going to see this graph that looks like this. It's going to come together right along the y-axis, but it's not going to ever touch the y-axis. The y-axis is going to be one of its asymptotes. So there is no y-intercept for this problem. For the x-intercepts, we got a lot of work to do here. So first of all, we need to factor the top and the bottom to do this. To factor the bottom, I would start by taking an x out of the bottom, bring it outside, and then I can see that it's just AC method. So I'm going to rewrite. So well, what have you guys done first, the numerator or the denominator?
I've done the denominator.
Denominators.
I've done the denominator.
All right, we've done both, I've heard. Okay. It doesn't matter which one I do first. I'm going to start with the numerator just because I heard more people say that. So for the x-intercept, we have to factor both. So factoring the numerator. Let's do this. To factor it, I want to find the roots really using my synthetic table. So doing so, I want to plug those numbers in accordingly. So here I'm going to have 1, negative 1, negative 19, 49, negative 30, right, Lauren? Okay? I'm going to plug a 1 in to start here.
Yeah, that's where.
Okay, test the 1 to start.
1,
1 by 1 is 1. 1 minus 1 is 0. 0, negative 19.
30.
Very good.
I used to.
Now, immediately, this tells me that that is a root. So one of my factors of my numerator is x minus 1. That's one of them. We have to write this down because, you know, I know the roots, that's great. But if the factors repeat themselves in the top and the bottom, it's actually a whole. So I need to know what the factors are. That's one of them. Now I'm going to make a subtable. With that subtable, I'm going to use these numbers. I'm going to go to my next number. Well, I should really test 1 actually, because it could be a repeated root. So I would start with 1. Okay, again, it could be a repeated root.
1,
1 by 1 is 1. 1 and 0 is 1. 1 by 1 is 1. 1 minus 19 is negative 18. Negative 18 and 30 is positive 12. So that doesn't work. But it doesn't tell me, they're not alternating signs, and they're not all the same. So it's not an upper or lower bound. So I can go up to 2, or I can go down to negative 1. It doesn't matter at this point, because I have no indication for my signs. Had my signs been alternating or consistent the whole way, I could have set upper limit or lower limit. So I'm just going to go to 2 for now. Bring down the 1. This is 2, and 0 is 2. 2 minus 19 is negative 15. Negative 30 and 30 is 0. So another factor is x minus 2. At this point in time, this becomes just simply x squared plus 2x minus 15. Well, how do I know that, you might ask? I start from the beginning. In the beginning, I had x to the 4th. When I get the first root, I get x to the 3rd. When I get the second root, I get x squared. Remember, every time you get another root or another factor, you're reducing the degree by 1. So it was x to the 4th to start. We found the first factor, it became x to the 3rd. We found the second factor just now, thus it is x squared. Trevon, what do I get when I factor these two?
No,
You had a question?
yeah, I did.
Well, what do I get when I factor them? You can do it.
X minus 3.
X.
X minus 3 plus 5.
Okay, and what was your question?
There's something that's, but I still came up with it.
Yeah, because 3 and 2 are both roots. You just happen to choose 2 to start with. That's fine. Right? Your answers are 3 and 2, aren't they, for the roots there?
Yeah.
And don't I have 3 and 2 as my factors here? That's where those are from. And now your resulting quadratic should say x squared.
Plus 4x minus 5.
Yep. Because that's these two factors. That's where those two come from now. So it shows you that it doesn't matter what order you use. So there's my numerator. Okay, that's my numerator alone. Now I need my denominator. We got 3 minutes where we can easily do this. Let's see. 2, 7, negative 4. 2, 7, negative 4. All right. Right away, what do I factor out of everything? Start with an x, please.
What?
You guys really need to focus for the next 2 minutes. Come on.
And then 18 method.
Here, for AC method here, I have to start by identifying AC. AC is negative 8.
It'll be 8 and negative 1.
Okay, B is 7. What numbers add up to 7, Derek? Good. 8 and negative 1. 8 and negative 1 add up to 7, and 8 and negative 1 multiply to negative 8. So I break this apart. I leave the x still. Remember, I break it into 8 and negative 1. I always start by breaking up the middle term into whatever it can factor into. Then I put my dashed line here. It's like a mental dashed line. You don't have to actually do it. I know this is an x here. What comes out of the 2x squared plus 8x? 2x. And I'm left with x plus 4. Well, over here I have negative x minus 4. What should I factor out? Negative 1. I need a negative 1 out of here so that I still have x plus 4 here. Remember, I want the x plus 4 in both spots.
Do we have to write it like that?
I want the x plus 4 in both spots. What do you mean, John? How else would you write it?
I didn't write it.
Well, your final answer needs to look like this. As long as your final answer looks like this. That's your final answer. Again, take a look. The x carried down the whole way. I didn't ignore it. Please don't. The x plus 4 that repeated itself becomes one of my two factors down here. The numbers that are on the outside, my GCFs, the 2x and the negative 1, becomes my other factor right here. As always, as we've done all year now, since we learned this many, many months ago. Okay, AC method has not changed, it's not going anywhere. If you don't know it, you gotta learn it. Here, for these three factors now, I've got those as my denominator. My numerator was from earlier, up here. Those are my 4 for my numerator. So I've got negative 1, negative 2, negative 3, 5. Negative 1, negative 2, negative 3, and 5. That was my numerator, my 4 factors. My denominator, quickly, notice, for this kind of a problem here, I don't have anything canceling. Do you see anything canceling here? X plus 4 doesn't cancel. The x minus 1s don't cancel here. So my 4 roots for this problem are going to be the top 4 here. Are going to be the top 4. Tonight your homework is to work on these problems. You're doing the same thing, except you're finding the x and y intercept for all of them. For all of them. Please make sure you practice. Your first assessment on this will be on Thursday. Your second assessment on concept 44, which is what you took today, will also be on Thursday. Will also be on Thursday.
Hey, Mr. Howe, we need another.
Say again?
We need another bit.
Who needs bigger? I give him one short, you an extra.
No, I didn't want to see that.
No, you did not see it.
Yeah.
She said?
She said, yeah, they go back to the past. No.
Put one bullet.
And then he was like, hey lady, can you put this Michael Jackson black? Like, oh,
Oh, yeah.